Hey guys, very quickly, we're going to focus on the law of definite proportion. Oh yes. Another name for the law of definite proportion is also called the law of constant composition. So once you just hear definite proportions, what are we referring to? Constant composition. Don't play with the two of them. And this is our lesson 2, right? Oh yes, very fast. And another important thing is that you must know that law of your definite proportion or constant composition is under the law of chemical combinations. And I told you that there are 4 laws of chemical combinations. What are the 4 laws of chemical combination? The first is the law of conservation of what? Mass or matter. And that was the first class where I explained everything, treated all the Jamb past questions and the Waec past questions for you. And this second law now is the law of definite proportion or your constant composition that we're going to focus on all through this class. The next class will be all about the law of multiple proportion. After that, I'm going to cap it up with everything about the law of reciprocal proportion. And I told you that the law of reciprocal proportion is not commonly used. Let's rock our second part, which is the what? Law of definite proportion or the law of constant what? Composition. Now, the first question. Who is this guy? Of course, it's not any other person than for us to look first into his origin, right? Of course, the law of definite proportion or constant composition is tied to Proust. So Proust in 1799, what year? 1799, he suggested the law of definite proportions. So who suggested the law of definite proportion? It was suggested by Proust in what year? 1799. What is the definition for the law of your definite proportion or your constant composition? It's a constant exam question for both Jamb and Waec. Now listen, the law of constant composition or definite proportion states that all pure samples, first and foremost, what do I need? Pure samples. All pure samples of the same chemical compound. In other words, all of them must be pure samples. Number 2, they must be the same chemical compounds. All pure samples of the same chemical compounds contain the same elements. The same what? Elements. The same chemical compounds, they contain the same what? Element, combined in the same proportion by what? Mass. If you know these 4 things, you know the definition. What to go? What is the law of constant composition or definite proportion? It states that all pure samples of the same chemical compounds contain the same elements combined in the same proportion by mass. All pure samples. Number 1. Want to go? Vibe it with me. This is a constant exam question. What is the law of constant composition or the law of definite proportion? All pure samples of a particular or the same chemical compound contain the same elements combined in the same proportion by what? Mass. Or another way we can better put it is that all pure samples of the same chemical compounds have the same percentage composition by mass. All pure samples of the same chemical compound, what happened to them? They have the same percentage composition by mass. Oh, you think I'm whining you? Look at the exam question now. Waec 1995 question 2. You can see that Waec adds an interesting question. And the question all the way says all pure samples, right, of the same chemical compound contain the same elements combined in the same proportion by mass. It's a statement of dash. Who made the statement? Of course, is it the statement of the law of your conservation of matter? Or it is a statement that you trace to law of constant composition? Or is it a statement of multiple proportion? Or it is a statement of your Gay-Lussac? Of course, this statement, all pure samples of the same chemical compounds contain the same elements combined in the same proportion by mass. Of course, is a statement of your what? Law of constant composition or your law of what? Definite proportions. And that makes option what? B, the correct answer. Right? What is the law of constant composition? Very fast. Give me the reason. We said that the definition of the law of constant composition is that what? All pure samples of the same chemical compound, they contain the same elements combined in the same proportion by mass. Or what is the second way you can tell us? All pure samples of the same chemical compound have the same percentage composition by mass. If this definition has not settled in you, don't go into any other thing. Very, very important. Let it settle. If you get that very fast with me, look at your Waec 2018 question 40. Waec brought this question as well. And the question all the way says, the law of definite proportion states that Shall you see that it's a constant question? The law of definite proportion states that. What does it state? Option A, all pure samples of the same compound contain the same elements combined in the same proportion by mass. That's number one. Option B says, very fast, pure samples of substances are in the same proportion by mass. Haha. Option C says, what is it? Chemical compounds are pure because they contain the same elements. Shall the wine. Option D now says that matter can neither be created nor destroyed. Now, what is the correct answer to this question? All pure samples of the same compound, right, contain the same elements combined in the same proportion by what? Mass. And that makes option what? A, the correct what? Answer. Right? Very simple. You can see that twice WAEC has brought this question, so it's very, very important. Another important thing very quickly is the experimental verification of the law of your definite proportion or your constant composition. How do we verify the law of definite proportion? How do we verify the law of constant composition? A lot of JAMB questions are loaded here. Now, I'd like you to follow me very quickly. Number one, pure samples of your black copper 2 oxide. So, we're going to be using your copper 2 oxide, which is your CuO, right? And this is what we're going to be using for our test, or true. So, your black samples or pure samples of your black copper 2 oxide. First and foremost, I want you to know that your copper 2 oxide, the color of it is what? Is your black. So how do we obtain the pure samples of this black copper 2 oxide? It can be obtained by 3 different chemical reactions. Please, how many chemical reactions? 3 of them. If you are ready to flow with me on this, let's go together very fast. Now, this is it. The reaction 1 that we can use to obtain pure sample of your black copper 2 oxide. Number 1 is action of heat on copper 2 triazonitrate 5. All I need is give me my copper 2 triazonitrate 5. What's the formula for copper 2 triazonitrate 5? It is nothing but your what? Your Cu then NO3, right? Into 2 like this, which is solid. This is your copper 2 triazonitrate 5. When I take my copper 2 triazonitrate 5, what do I do to heat? I'm going to heat it. That's why we say action of heat on your copper 2 triazonitrate 5. When I apply heat to copper 2 triazonitrate 5, it's going to decompose into my black sample of my copper 2 oxide. Your nitrogen dioxide, which is your nitrogen 4 oxide, which is your NO2. And then my oxygen gas will be above alongside with it. So take your copper 2 trioxonitrate 5, right? When I heat copper 2 triazonitrate 5, CuNO3, open your bracket 2. When you heat it, what will happen? It will break down and decompose into your copper 2 oxide, which is black, right? Your nitrogen 4 oxide, which is your NO2, and your oxygen gas. This is one way or one of the reaction I can obtain my copper 2 oxide. Pay attention to the listing. The second way, very fast, which is the reaction 2, is the action of heat on copper 2 trioxocarbonate 4. Sir Peter, give me copper 2 trioxocarbonate 4. The formula is your CuCO3. So your CuCO3, this guy is also solid, is your copper 2 trioxocarbonate 4. When I apply it to my copper 2 trioxocarbonate 4, what is going to happen there? It's going to decompose and it's going to give me black sample of my what? Copper 2 oxide, and my carbon 4 oxide gas will be involved. What I'm interested in majorly is the black sample of your what? Your copper 2 oxide. That's what we are interested in. Pure sample of black what? Copper 2 oxide. If I get that, I'm out of there. The third equation, very fast, right? That is going to give me my pure sample of black copper 2 oxide is what? The action of heat on copper 2 hydroxide. So when I take my copper 2 hydroxide, which is my CuOH like this too, and then this is solid copper 2 hydroxide, and then I apply what? Heat to it, it's going to break down and decompose into my black, my pure sample of your what? Your black copper 2 oxide. And then steam is going to be evolved. The steam there, of course, that's your water there, right? Steam, gaseous form, is going to be evolved from it. So these are the 3 primary reactions or 3 basic reactions that I'm going to use to obtain my pure sample of my copper 2 oxide. Does it make sense now? Are you following me? Do you understand this? If you get it very quickly, First, I'd like you to hold this tight and understand this with me. There is an explanation of the law of constant composition that was given by your Dalton atomic theory. Come, let's go. So, Dalton atomic theory was given by who? John Dalton. The law of constant composition was given by who? Proust, right? In what year? 1799. Now, how does the law of constant composition, right? How does he explain Dalton's atomic theory? Or how does Dalton atomic theory explain the law of constant composition? Now, this is what we're going to explain. First, I'd like you to note this, that all the atoms of an element are alike in three things: your shape, your size, your mass. All the atoms, right, of an element. Let's say, for example, we are taking hydrogen. If you like, take hydrogen from Nigeria, or hydrogen from Ghana, or hydrogen from UK. All the atoms of an element in as far as the hydrogen, they are alike in three things. They are alike in size, they are alike in shape, they are alike in what? Mass. But differ from the atoms of every other element. You see, this is one of the 5 postulates that John Dalton gave in his atomic theory. In John Dalton's atomic theory, as we move down in the series of classes, you are going to see your Dalton's atomic theory very quickly. John Dalton gave 5 postulates in his atomic theory. And one of the postulates is where he said that all atoms of an element are alike in size, 1, they are alike in shape, and they are alike in mass, but differ from atoms of every other element. You see this statement that Dalton gave. This is the statement that validates or supports the law of constant composition by mass. What is the law of constant composition by mass? The law of your constant composition states that all pure samples of the same chemical compound, what do they contain? They contain the same elements combined in the same proportion by mass. Or all pure samples of the same chemical compound have the same percentage composition by mass. You see, this statement or this definition of the law of constant composition was validated by John Dalton. Follow me. Hold on a bit. The complete series of classes, right, as far as your syllabus is concerned regarding your Jamb And Waec, everything has been covered in details for you in the LearnLift app. And guess what? The sweet part is that you have access to your CBT, right? You have access to your video lessons, you have access to your notes, you have access to your past questions. Everything from the beginning to the end is directly in the LearnLift app for you. So all you have to do is just mark down to Play Store or App Store and download the LearnLift app, where you follow all your classes from the beginning to the end. A quick one before we move. Let's get back to class. Enjoy. Look at Jamb And Waec question. It's a constant exam question that Jamb And Waec have asked, and the question went ahead to say, which statement from Dalton's atomic theory helps to validate the law of constant composition? That's what the question is saying. Which of the statements from Dalton's atomic theory will validate the law of constant composition? Option A says atoms are indivisible and indestructible. No, this is not true. This one is talking about the indestructibility and the indivisibility of atom. And we know that that's wrong, right? Because of the discovery of your electron, your protons, and your neutrons, which are the fundamental subatomic particles. Look at the second thing. Atoms combine in simple whole number ratio to form compounds. That's not true. Option C says all atoms of a given element are identical in your size, in your shape, and your mass. Making sense. Option D says different elements have different types of atoms. That's not where we are going to. Which statement from Dalton's atomic theory help to validate the law of constant composition? The statement that validates it is that all atoms of a given element, they are identical in three things: your size, your shape, and your mass. That makes option what? C the correct answer. Does it make sense now? Keep your okay now. Please, there's what is called your gravimetric analysis. What did I call it? Gravimetric analysis. They don't play with this. I gave you 3 reactions that you can use to obtain your pure samples of your black copper 2 oxide, right? Yes. So we're going to carry out gravimetric analysis, right, on those 3 pure samples that we have looked at. First and foremost, what is gravimetric analysis? You must note this, that gravimetric analysis is just an aspect in your quantitative analysis. So inside quantitative, there's what is called qualitative and quantitative analysis. As we move on, we teach you all of these things. Your quantitative analysis is different from qualitative analysis. Inside quantity, the one that is quantitative analysis, we have what is called gravimetric analysis, which is an aspect of it. And gravimetric analysis involves the weighing of masses of reactants and products of chemical reaction. Let's go together. What is gravimetric analysis? Gravimetric analysis is an aspect of what? Quantitative analysis that involve the weighing of masses of reactants and products of what? Chemical reactions. So once they give me chemical reactions, and I have to go and carry out the weights, right, of the reactant and product to determine their weight. Please, what do we call that? It's called gravimetric analysis. So as we move together, we're going to be doing some weight measurements. Now follow me and look at gravimetric analysis in those 3 reactions. And what are the 3 reactions I gave you? Number 1 is the action of heat on your copper 2 triazonitrate 5. Take your copper 2 triazonitrate 5, CuNO3, right? Heat it. What will happen? If I apply heat to it, it will decompose into my what? Pure sample of your black copper 2 oxide, your nitrogen dioxide, which is your nitrogen 4 oxide, and oxygen gas, right? What are we interested in there? We are interested in the pure sample of our what? Black copper 2 oxide. Second reaction, very fast, is the action of heat on your copper 2 trioxocarbonate 4. Take your copper 2 trioxocarbonate 4, which is your CuCO3, right? Apply heat to it. When you apply heat to this, it will decompose and give you pure sample of your black copper 2 oxide, right? And then carbon 4 oxide gas is going to be evolved. Nothing concerning me and the carbon 4 oxide gas. All I'm interested in is the pure sample of your what? Your black copper 2 oxide. And then the reaction theory I gave you as well is the action of heat on copper 2 hydroxide, right? Very important. So you follow me. When we apply heat to your copper 2 hydroxide, what is going to happen? Your copper 2 hydroxide, CuOH2, right, is going to decompose once heat is applied into your pure sample of your black copper 2 oxide, and your what? Your steam is going to be given out. Not that you're just going to say water. This guy is not liquid. That's steam that you have there. Right. Now, this is what you must understand. If I have these 3 reactions, sir, how do I apply gravimetric analysis on them? Now, follow me. And then we're going to look at it. See here, I've told you before that these exams are not difficult. No. If you are well taught, right, you are going to do excellently well. The only thing I need from you is your undiluted attention. So, because if you are easily distracted and not go like calm, I just tell you. Now follow me, let's go together very fast. You must understand is that if I'm carrying out my gravimetric analysis on the reaction 1, reaction 2, reaction 3, right? What happens there? First and foremost, I draw your attention to this, that each pure sample of your copper 2 oxide, right, from all of those different reactions is weighed separately. So I will weigh reaction 1, weigh reaction 2, weigh reaction 3. And then you now place them into what is called your Pecolin boat. What is it called? Pecolin boat. And that Pecolin boat, right, is placed in a combustion tube. First and foremost, this is your combustion tube, right? So the pure samples of your copper 2 oxide, all of them must be pure. I have weighed them separately, right, in a what? A Pecolin boat that is placed inside my what? Combustion tube. Are you seeing it now? And that's not all. I will now start to reduce them. So reduction is going to now start taking place, right, in a stream of hydrogen. Please, what is happening there? Reduction is taking place in a what? In a stream of what? Hydrogen. To produce reddish brown residue of copper metals. Oh, listen to me. All the reaction 1, reaction 2, reaction 3. You know, what do I have there? My pure samples of my black copper 2 oxide. I'm now going to be adding hydrogen to it. And we said that the addition of hydrogen to a substance is called what? Reduction. If I'm adding hydrogen to it, that is reduction. And what will happen? That hydrogen that is added will reduce that pure sample of black copper 2 oxide into your copper metal. Once I am obtaining my copper metal, how do I know that it's copper metal that is now being formed? Because the color is going to change from black copper 2 oxide to reddish brown copper metal. Just the listing, they follow me. Once this is taking place, what am I going to reduce that copper 2 oxide into your copper metal? Of course, that's your what? Hydrogen. So I'm going to be applying, I will allow hydrogen to be flowing into the whole of this reaction. Please allow the hydrogen to keep flowing, right? Until the entire reaction cools down, and then I will now reweigh it at the end of the day. Look at it. This is where we are heading to. It's very simple. First and foremost, what do I need there? Your copper 2 oxide, which is the solid, which is the pure sample of black copper 2 oxide. All I will just apply, I will start blowing hydrogen into the entire reaction, from reaction 1, reaction 2, reaction 3. Let hydrogen be passing through all of them. And this is the hydrogen gas there. As the hydrogen gas is passing through them, this hydrogen gas, addition of hydrogen to this your copper 2 oxide, that's reduction. It will reduce the copper 2 oxide into your copper solid. Sure, you see it now. And then steam is going to be produced at the end of the day. Oh, first, let the equation be in your copper 2 oxide. When I add hydrogen to it, is your oxidation or reduction? Reduction. What is it going to give me? It's going to give me my copper solid and my what? Your steam at the end of the day. Okay, now follow me. Let me show you something. How do I know that my copper solid is formed? Because of the color change. The color will change from what? Your black. Your copper 2 oxide is black. It has changed to what? Reddish brown or brown copper. That means it has been what has been formed there. Copper solid has been formed there. Very easy and direct. And another important thing, please, I like you to note this very, very fast and important. Number one thing I like you to note is this. Experimentally, the combustion tube should slope forward. Look at this combustion tube now. Look at it very well. If you watch, it is tilted downwards, right? Why is this sloping forward? Very, very well. It is sloping forward for 2 reasons. What are the 2 reasons? Number one, so that the stream of hydrogen gas should be allowed to flow over the residue. In other words, because it is tilted, you see, all through in the whole of this setup now, I can now have my hydrogen gas flowing all through in the whole of this residue. Does it make sense now? Now, as the hydrogen gas is flowing all through the entire residue, number one, please allow that hydrogen to keep flowing until it is cold. What happened? If the hydrogen is flowing all through it until it is cold, it will prevent re-oxidation of the residue by the steam that is formed. Follow me, let me show you something. Your copper 2 oxide, right? Yes, solid. I'm adding hydrogen gas to it. What is it going to give me? It's going to give me nothing but my what? My copper solid, which is reddish brown or brown in color, plus my what? Steam, which is your H2O, gaseous form. That's the steam there. Now, this my hydrogen gas that is passing over my copper 2 oxide solid, allow the hydrogen gas to keep flowing. If you stop it any point of the reaction, what will happen? Any of the steam that is already being formed, the steam there will go back and combine with your what? Your copper. And when the steam is combining back with copper, that is oxidation taking place. So in order for us to prevent re-oxidation of the residue by the steam, allow that copper to allow the what? Hydrogen gas to keep flowing all through until the entire reaction cools down. If you have obtained that, that means you are good to go very fast. Now, please look at your Jamb And Waec question that they asked from this. The powerful question all the way says, what is the primary reason for allowing the steam, right, or the stream of hydrogen gas to flow over the residue until it is cold in the experiment to reduce copper 2 oxide into your what? Copper. Why are you allowing the hydrogen to flow over it? This is a constant exam question. Option A is to speed up the reaction process. Well done, the catalyst. You are very, very wrong. It's not true. Option B says to prevent the residue reacting with the steam and becoming reoxidized. Making sense. Option C says to ensure complete combustion of hydrogen gas. That's not true. Option D says to cool the combustion tube readily. Why are we allowing the hydrogen to pass through it? To prevent the residue from reacting with the steam, right, and becoming reoxidized. That makes option what? Be the correct answer. I explained it to you that the reason is very simple, right? What happens here? allowing the stream of hydrogen gas to flow over the residue until it cools. It will ensure that no stream or no steam is present, because you know the reaction CuO, right? Solid, if it combines with your hydrogen gas, you allow it to keep flowing until your Cu solid is formed completely, and then your H2O, this guy is what gas that is formed there, right? Please, if this guy at any point go and combine with this thing, what will happen? They will reoxidize readily. And when they reoxidize, what happen? Of course, then before you know, you are going to obtain your what? Your copper 2 oxide back, and then it's going to affect the purity of the what? Of the copper that you are trying to what? Obtain at the end of the day. So that's just the main reason. Look at another question very fast. A Jamb Waec question. Jamb has asked it, Waec has asked it. And the question all the way says, why should the combustion tube slope forward during the reduction of copper 2 oxide to your copper? Why should this slope forward? Option A says to facilitate the flow of hydrogen gas, to facilitate it. Option B says to allow for easy collection of residue. Option C says to prevent water forming during the reaction from flowing backwards and reoxidizing the copper. Option D says to improve the visibility of the reaction process. The major reason is to prevent reoxidation. That's the major thing we're trying to prevent. Option what? C becomes the correct answer. Does it make sense now? If you get this, that means you are doing very well. And what was the reason we said? Sloping the combustion tube forward, we ensure that any water that is formed as a byproduct of the reaction is what? Carried away from the reaction site, right? By what? Gravity, gravimetric analysis. Preventing it from coming into contact with the reduced copper and causing what? Reoxidation. This is the answer. If you get this very fast with me, still in this class that we are flowing with very fast under the law of your chemical composition, right? For definite proportion, guess what? In the next class, I'll take you around the calculations in the law of definite proportions, or your what? Constant composition. So we're going to be looking at all the calculations, all of them from beginning to the end. They are Jamb and Waec past questions, and we're going to be looking at all of them one by one. I'll see you in that class. Enjoy. Bye-bye. Hope you've enjoyed this class. Guess what? To follow up for more classes, just download the LearnLift app, whether on Play Store or App Store, and then follow up your classes. You must do extremely well. I'll see you in class. Bye-bye.